Hi everyone, I am Sun from Tsinghua University. Today I will present Scalio, a DPU-based JBOF key-value store, and share the ideas and techniques for addressing a scalability bottleneck in such high-density storage systems. On behalf of all co-authors, we would like to thank the Dengfeng Fund for supporting this work. Okay, the background of our work is clear. Modern online services, from social media to e-commerce, require key-value stores that can handle a large amount of data within short response time. These systems demand both high throughput and the ability to scale to large capacities efficiently. Let's compare the traditional storage server architecture with the emerging DPU-based JBOF architecture. Traditional storage servers typically uses CPUs, DRAM, and SSDs for storage and NICs for providing online services. But it comes at a cost of high power consumption, often 300 to 500 watts per CPU. In contrast, a DPU-based just a bunch of flash server or JBOF server uses more dedicated ARM cores for serving storage systems and can link to up to 36 SSDs through PCIe. Its energy consumption is much lower, around 75 to 150 watts. As we can see, using the DPU-based JBOF servers under a high-density configuration can provide the highest energy efficiency in terms of I/O per joule. Actually, vendors like Supermicro and AIC have started building high-density platforms combining DPUs like NVIDIA's BlueField-3 with up to 36 NVMe SSDs per node. This is a leap in storage capacity per DPU. But with this density comes a challenge how to efficiently process the I/O without overwhelming the relatively weak ARM cores on the DPU. As we'll see next, CPU saturation quickly becomes a bottleneck. We ran a simple FIO benchmark while gradually increasing the number of SSDs in the node. The results were clear. As SSD count and consequently IOPS increases, the CPU usage also increases. However, DPUs only have a small number of ARM cores, typically 8, with relatively weak computation capabilities. Therefore, handling I/O on the DPU's ARM cores will reach a bottleneck in computation. Lead, a prior key-value store optimized for DPU-based JBOF setups, addresses these challenges to some extent. It makes the best use of the ARM cores' computational resources, reconstructs the I/O workflow to minimize the CPU overhead, and achieves 800 kilo-QPS and a 4 SSD configuration. It actually saturates the SSD IOPS. However, when scaling up to more SSDs, lead hits a performance ceiling because the ARM cores again will become the bottleneck. This diagram shows lead's performance limitation when increasing the SSD count. We monitored the lead's actual CPU usage for handling SSD I/O with perf, filtered out the usage for RDMA network and metadata management, and plotted this figure. It can be seen that the bottleneck of scaling up is the limited ARM cores for SSD I/O processing. So to truly scale up, we need a new approach, one that bypasses the ARM cores as much as possible. Before diving into our offloading strategy, let me briefly introduce the NVMe-oF, NVMe over Fabrics, or called NVMe-oF. It is a standard protocol that allows remote access to NVMe SSDs over high-speed networks like RDMA. In a typical setup, incoming NVMe-oF commands are handled by the server's software stack. They go through the NIC, then into the kernel's NVMe-oF target module, and then to the NVMe driver, and finally to the SSDs via PCIe. Thus, this consumes CPU cycles and becomes a bottleneck under high I/O load. The NVMe-oF target offload, on the other hand, offloads the NVMe I/O handling entirely to the ConnectX NIC hardware. The NIC internally handles the NVMe protocol. and issues them straight through the SSD through PCIe peer-to-peer. So no CPU or DRAM is involved. This lets us fully bypass the ARM cores, offloading all the SSD I/O handling to the NIC. This offload path matches the throughput of the standard normal strategy based the standard normal one, but requires 0 CPU usage. So this is the key to Scalio's scalability, allowing us to support more SSDs without overwhelming the DPU cores. Scalio is designed around the principle for minimizing CPU usage while maintaining correctness. We use the DRAM on the DPU as cache for fast path reads, and we use one-side RDMA operations to read the hot items. For the items that do not exist in the cache, we use NVMe-oF target offload to read the data from the SSDs. In both cases, the DPU's ARM cores are bypassed. For write operations, we further reduced the CPU usage with a batched writing mechanism. It reduces the CPU usage as fewer SSD I/O will be actually issued. But this raises a new challenge. How do we ensure the linearizability across clients, SSDs, and cache without the CPU involvement from the server side? Since clients issue operations directly to the storage system without server involvement, and they do so in parallel, the lack of coordination can lead to stale reads, lost updates, and inconsistent system state. Caching further complicates the situation, as read operations that refills cold data to the cache and write operations, they may both mutate the cache. So we need a new mechanism to ensure that all clients see a consistent, linearizable view of the data. Consider this case. Initially, X is missing in the cache. Then two clients issue operations at very close time. Client 1 reads the data X from the SSD and then refills it into the cache. Client 2 writes X with a new value. The question is, when should the new updated value be visible to other clients? We give two counterexamples. One approach may be updating the value first to the cache and then to the SSD. However, consider the case where a third client in this figure evicts X as the very moment. This will make the update lost. So actually, the update at this time period will be lost because the previously written X to the cache has been evicted. On the other hand, another approach is writing the value to the SSD first and then use the invalidate path later on. However, there may still be a short time window between the update and the refilling. So consider the client 3 and client 4 that issue read operations at these two moments as illustrated on the figure. It can be seen that the order of the readings are wrong. First read X is 43 and then X is 42. So these operations cannot be linearized. The key to the problem is that the DRAM should be aware of the filling process. Our solution introduces an intermediate incomplete state for every cache slot. When a client reads a missing key, it records an incomplete state in the DRAM and then starts fetching the data from SSD using NVMe-oF. Other clients encountering that key know that the data is being fetched. This coordination ensures correctness without central CPU involvement. Take Scalio's data flow on cache miss as an example. It first tries to read the data from the cache with RDMA read, but find no matching slot. It will then pick a victim, and then it will lock the slot with RDMA-CAS. This operation actually marks the slot as incomplete at the same time. Then it will read the actual data from the SSD with NVMe-oF target offload, and then fill back the cache with RDMA write. The key the key point in the sequence is to first mark the slot as incomplete and then refill. And this process bypasses the ARM cores. When it comes to the implementation in data structure, Scalio uses this logic. This logic uses 2 bits in the slot. One is occupied for indicating the validity of the slot, and the other is the complete flag for indicating there is an ongoing refilling process. And these 2 bits make the 4 states. Here comes the 2 incomplete states, where any other reader to the same key should wait until refilling is done. This is managed entirely via RDMA and ensure that updates and reads will not cause a race condition, and no CPU coordination from the server side is required. Now comes the evaluation part. We evaluate Scalio on a test bed with 1 server node containing 7 Samsung SSDs. We test with up to 5 client nodes to saturate network ALPs under some workloads. We limit the resources to 8 CPU cores and 8 GB DRAM to match the typical settings of a DPU. We compare against lead, the SATA key value store on DPU-based JBOF platforms, as we introduced earlier, and lead plus Ditto. Ditto is a disaggregated key value store, key value cache that serves as a cache component add-on to lead for fairness. We perform our evaluation under 5 YCSB workloads. Workload E is a range query that we do not consider. Take the most significant workload, YCSB-C, as an example. Scalio outperforms the baselines on YCSB workload C, which is a read-only workload where the benefits of Scalio gets maximized. This demonstrates how effective RDMA reads and NVMe-oF target offload are. But not only for workload C, this trend also holds across all workloads A through F. Scalio consistently scales up with the number of SSDs fully utilizing available SSD ALPs while the baseline flatten or degrade. This can be attributed to the joint efforts of the offloaded read and the batched write and the RDMA cache. And we also provided an improvement breakdown experiment. Each component of Scalio contributes to its performance. Together, they lead to Scalio's scalable performance. We further talk about latency under workload A. As can be seen, Scalio without a batched write, the red line, can perform higher throughput with lower latency compared with the baseline. It is the brown line. Scalio can also achieve even higher throughput with slightly higher latency, as can be seen from the blue line. This means that Scalio has a benefit in latency. And this also offers a chance for users to tune their behavior, to tune the config based on the application's requirements. And actually, under all workloads, Scalio maintains a generally lower latency than the baseline system. Finally, we test Scalio across various configurations: skewness, record count, and the number of cores. And we demonstrated the result under YCSB-C. In all workloads, Scalio outperforms the baselines, demonstrating that its benefits generalize. Although the figures on the slide are only for workload C, Scalio consistently outperforms the baseline under all workloads, and you may refer the paper for detailed results. That concludes my talk. Scalio shows that with smart offloading and coordination, we can scale DPU-based JBOF systems efficiently without offloading CPUs or sacrificing consistency. And thank you for your attention, and I'm happy to take questions.